Marking is the first and most crucial step in the major garbage collection cycle. In this video, we will discuss the tricolor approach to the marking process, and we will also take a closer look at all the techniques that JS utilizes to make this much more efficient, so the interference in the regular code execution is minimized. Hi, I am Rohan, and this video is part of a series of videos where we are exploring how JS manages its memory in depth. So let's get to it. What is tricolor marking? This algorithm is used as an enhancement to a previous marking algorithm where each object is marked either as a live or a dead object. Here instead, each object is marked with three different colors. V8 employs a marking method which utilizes two mark bits for each object and something called marking work list. These two mark bits represent three different colors: white with 00, gray with 10, and black with 11. Now, what does each of these three different colors mean to the collector? The first color is white. When an object is created, then it is set to white, which signify it as a new object, which also means that the collector has not yet visited this object. But when the garbage collection process starts, then these objects can be safely considered as objects that are no longer referenced and are hence dead objects. The collector can safely sweep these objects, and hence these objects are also known as condemned objects. The second color is gray. Gray objects are those objects that have been visited by the collector at least once and its reference have been pushed into the marking work list. But the collector has not yet examined its references to other objects. When the garbage collection starts, these objects are also considered to be dead objects and can be deallocated. The third color is black. Objects marked as black are those objects that have been visited by the collector and its references to other objects have been visited too. An important thing to note here is that black objects do not contain any references to white objects. From the perspective of the garbage collector, these objects are considered to be live and are hence retained. Now, initially, all objects are marked as white, indicating that the collector has not yet identified them. A white object transitions to a gray object when the collector discovers it and adds it to the marking work list. When the collector removes a gray object from the marking work list, uses the references within this object to visit all the neighboring objects and processes them, then it changes the color of the object from gray to black. This process is known as tricolor marking. The marking process concludes when there are no more gray objects in the marking work list and the remaining white objects are considered to be unreachable and can hence be safely swept. Let's look at the algorithm in detail. When the marking process starts, then all the roots are fetched. After that, we iterate through the roots one by one and mark each one of them. This will call the mark function with reference to the root. Inside mark function, we will get the mark bits of the object and check if the mark bits are white or not. If it is, then we will set the mark bits to gray and then we will push the reference to the object in the marking work list and return. Also, if it is gray or black, then we won't enter into the condition and simply return. When all the roots are marked and we have an initial marking work list, then we will call the mark worklist nodes function. Inside this function, we iterate through the nodes in the marking work list one by one. We of course iterate using a loop. When we enter inside the loop, then we set the mark bits of the node to black and then get all the references to the subnodes from the node. Then iterate through the subnodes one by one and mark each one of them, which means we call the mark function with reference to the subnode and check if the mark bits of the subnode is set to white. If it is, we set it to gray and push the reference in the marking work list and return. Otherwise, we just return if it is gray or black in cases of already visited nodes or circular references. When all the subnodes are marked and the work list is updated, then we repeat the process till all the nodes in the marking work list is visited at least once and the nodes are set to black and there are no more gray objects. Then we return. In the main marking function, we wait for the next marking cycle and then repeat the process. Let's visualize the tricolor marking with an example. When we run our code, then we create a bunch of objects during the course of our execution. So they are allocated in the heap and are linked to each other using references. and the root object's reference is stored in the stack. There are also some objects whose references are removed from the stack because they are no longer needed for various reasons. Then, at some point in time, the marking process starts. So the root objects that are accessible from the stack are immediately marked as gray and are pushed into the marking work list. Then these root references are popped from the marking work list one by one, marked as black, and are used to traverse to other linked objects. Those linked objects are marked as gray and their references are pushed into the marking work list. And this process of popping a node reference from the marking work list, marking it as black, and then subsequently reaching and marking other neighboring nodes to gray and pushing their reference in the marking worklist continues till all reachable nodes are marked as black and the marking worklist is empty. Then the remaining white objects can then be safely swept or compacted. So how does V8 makes this more efficient? Since we know that running the entire marking process all at once after a large number of allocations pauses our main application down for several hundred milliseconds. A clever solution to this is to do the entire marking process incrementally, which means that instead of a single long pause, the entire marking process is split into smaller chunks and our main application can run in between those chunks. The collector determines the amount of marking work in each incremental chunk is directly based on the allocation rate in our main application. Typically, this significantly enhances the application's responsiveness. However, in case of a large memory heap under substantial memory constraints, there can still be extended delays as the collector tries to keep pace with the allocations. But there is a problem. When we do incremental marking and then our main process resumes and it changes the structure of an already visited object, like assigning a new object to an existing object's field, which will definitely cause inconsistencies such as retaining a dead object or deallocating a live object. To resolve this, every time we change the structure of an object, we need to inform the collector by calling a function known as write barrier. Let's look at the write barrier algorithm. When we assign an object to another object's field, then we call this function with object, field and value, which is also an object. When we enter into the function, then we will get the mark bits of the object and the mark bits of the value. After that, we will check if the object's mark bits are set to black and the value's mark bits are set to white. If this holds true, then we will set the mark bits of the value to gray and push it into the marking work list and return. This ensures that there are no black objects that are pointing to white objects, maintaining the strong tricolor invariant. This will make sure that the application cannot conceal a live object from the garbage collector. As a result, any white objects that are remaining at the end of the marking process are genuinely unreachable from the application and can be safely released. Browser's task scheduler schedules small incremental marking steps during the idle times in our main thread without causing any long pauses. This optimization is highly effective when there is some available idle time. However, due to write barrier's cost, the incremental marking may actually reduce the overall application's throughput. Why do I say that? Take a period in time and sum up all the time it takes to do incremental marking plus write barrier and compare it to the time that it would have taken if we had done the entire marking process all at once. Then this duration is greater than regular marking, which means that the overall application's throughput is slightly reduced. To enhance this throughput and reduce the pause times, we need to utilize additional worker threads. There are two approaches to perform marking on worker threads: parallel marking and concurrent marking. Parallel marking occurs both in the main thread and in the worker threads, leading to a pause in the main application process during this phase. It essentially represents the multi-threaded version of stop the world marking. Concurrent marking, on the other hand, takes place on the worker threads, which allows our main application to keep running, and the marking is in progress concurrently. Now, V8 does something interesting. It combines the concurrent marking with the existing incremental marking process. So, in the main thread, the code execution and the marking process in chunks are done alternatively. And concurrently, the marking process is also performed in the dedicated worker threads. This way, the work of marking is shared among all the threads until all the objects are marked and the marking work list is empty, and a finalization step in which all the routes are checked again just to see if there are any more additional white live objects that were missed earlier. This step also leverages the worker threads just to speed up the process. Anyway, let's look at the flow to understand this process better. Assume we have 3 threads to work with, one main and 2 worker threads. In the main thread, the process execution happens for some time, and during this time, objects are being allocated in the heap. So, marking process starts concurrently in the worker threads. Periodically, a check is being made to see if there is any idle time. If there is none, then the main process continues. But if it does find some, then a chunk of the marking process happens in the main thread as well. After some time, the main process resumes until there is another idle time available. And this process repeats alternatively in the main thread. Now, after some time, the marking process is complete in all 3 threads, which means that the marking work list is empty and all the objects are marked black. So, a final marking process starts just to make sure there are no more live white objects. And after that, sweep or compact process happens. Now, we are not going to get into how this is actually being done since V8 has to deal with concurrency, making it thread safe, synchronization via atomic operations, etc., which is getting out of scope. And frankly, I do not have the necessary knowledge to get into this topic with you. If you want to know more about this topic, there are several articles on it in the V8 website. You can check them out. I will put the link down in the description. So, to summarize, we discussed what tricolor marking is, understanding its process in detail, and we also visualized it with an example. After that, we discussed the incremental marking process and a need for right barriers during the normal execution intervals in between the marking processes, which revealed to us the limitations of the incremental process, which led us to discuss ways to enhance the incremental marking even further by discussing parallel and concurrent marking and how V8 combines them into a single process which ultimately enhances it. We also discussed this incremental parallel concurrent marking process by understanding the flow of this process. I also want to discuss the sweep and compact process in detail with you. So this is what we will discuss in the upcoming couple of videos. Thank you for your time. Have a nice day. Namaskar.